The origin and direction of magnetic fields. In 1820, while searching for a relationship between electricity and magnetism, Hans Christian Ørsted noticed that a compass needle would be deflected away from pointing towards the North Pole when he connected a wire to a battery, and once he disconnected the wire, the compass would return to pointing north. Now the story goes on this when he actually did this as a lab in his classroom. He was a teacher, and whether he expected the result, whether he had put the compass there on purpose, that's really not known, but it's one of the most amazing discoveries ever found in a classroom. So what Ørsted deduced from that is that an electric current had to produce a magnetic field that would affect the compass needle more strongly than the Earth's magnetic field. And as if this wasn't enough, later on Ørsted produced aluminum for the first time, which was later used to carry currents sometimes in households until it was found to be not terribly safe. Here's a picture of Hans Christian Ørsted. He was a physicist and a chemist, and note the order in which I put them. And one of the most important statements in the history of physics: electric currents produce magnetic fields. So we have a current carrying wire here. See this blue guy here coming out of the page, and you're going to have to get used to terms like out of the page, into the page, because magnetism is going to bring a third dimension into our problem solving here. Electric fields we pretty much handled in 2D. Magnetism is going to require 3. And you see the wire, currents flowing out of the board, and magnetic field lines are created around the wire. In this case they're going counterclockwise. And you can see here where there's a magnet, and the magnet is aligning itself with the magnetic field lines. It has been experimentally observed that the direction of the magnetic field depends on the direction of the electric current. For example, you see over here that we have the magnetic field curling around the wire going in a counterclockwise direction. We just as easily could have said, well, why isn't it going clockwise? Well, because physically it doesn't. Experiments showed that the direction is as we've drawn it here. One way to come up with that is using the right-hand rule. Another way is to use vector calculus, which is a little beyond the scope of this course. So what you do, you'll have a wire drawn on a piece of paper here, and you'll put your right hand around it. See how you curl your fingers around it? And actually curl is a term for vector calculus, so I'm pretty sure that's why we're using it here. But you can see the fingers curling around so the tips of your fingers touch the palm of your hand. Now, the direction that your thumb is pointing is the direction of the current. See how the current goes up? Your thumb goes up. And now watch your fingers as they curl around like this. Look at the magnetic field. It's doing the exact same thing as your fingers. In this case, it's going in a counterclockwise direction. Magnetism was first observed when objects were taken out of the ground like magnetite and they attracted other metallic type items. Now, what's the value of this? We can take an iron core, and it's certainly magnetic, but it will not attract other pieces of iron. But if we run wires around it, the wires circulating around the iron core will create a magnetic field, and that is called an electromagnet. Many industrial uses are found for that, and this is a picture from, let's see, it looks like the early 1900s. We have a solid core of iron, you've got wires around it, and then up here right here you've got connections to electricity. So when you turn the current on, you have a magnetic field, and you can see these bits of metal being attracted to it. You can then swing this crane over somewhere else, you turn the electricity off, the magnetic field disappears, and all the scrap metal falls away. Earlier we stated that when a magnet is cut in half, and those pieces are cut in half, and those pieces are cut in half, and this is continued all the way down to the atomic level, assuming you had a knife that sharp, which of course this is more of a thought experiment than anything else, then each piece would still have a north and a south pole. The reason for this is that the movement of the electrons in the nucleus can actually be viewed as tiny electric currents. As you remember, currents are the movement of charge, and electrons are charge, and it's moving. And as shown by Ørsted, changing electric currents generate magnetic fields. So all the way down to the atom, you have basically it's acting as a magnet with a north and a south pole. Earlier I talked about the three-dimensional nature of magnetic fields. Well, you could see it on that current carrying wire that we just covered, where the magnetic field went in circles around it. So, electric fields we can very easily understand on two-dimensional paper. The electric field, of course, is three dimensions. It looks like if the electric field originating from a charge goes out into a sphere shape, so it's three dimensions, but we can get the idea of it by just drawing it in two. However, with magnetic fields, we need to introduce a third dimension to the paper. So we have left and right, that's easy, and then we have up and down. So far, nothing's changed. So we need a convention to represent the third dimension on a piece of paper, and we'll do that on the next slide. We're going to picture the magnetic field line, which is a vector that has magnitude and direction. We're going to picture it as an arrow. The head of the arrow will be in the direction of the field, so that's this side over here, and here's the tail of the arrow. Actually, Walter Lewin, who's a very famous astrophysicist and a very famous lecturer at MIT, carries an arrow made out of wood about 2 to 3 feet long in his classroom, and he uses it for a demonstration to explain how we'll show three dimensions on paper. We don't have that here, but let's take this arrow, point it away from you so you can see the tail feathers. Kind of looks like an X. So when you see X's, this shows a magnetic field that is pointing into the page, so it's getting us that third dimensional feel. If this arrow were pointed at you, which is never really a comfortable feeling, you'll see a dot. You'll see the point of the arrow. So when you see a range of dots like this, this is a magnetic field coming out of the board or out of the piece of paper. Here's our first example of how to use your right hand to determine the direction of a magnetic field. We have a current carrying loop. This is in the plane of the paper, so this is still showing in two dimensions. I want to find the magnetic field inside here. I've already drawn it here, but let's see if we can figure it out. I take my hand, take the right hand, put the thumb in the direction of the current, and the current is flowing counterclockwise around the loop, and actually I could grab this loop at any point and it would give me the same answer, but I'll grab it over here to the right. My thumb is pointing in the direction of the current, and again it's the tangent to the circle right here. My thumb points that way. I grab the loop, curl my fingers from the straight position until they touch my palm, and inside the loop the direction of my fingers are actually coming out of the piece of paper, so you can see I have the dots here. It shows that the magnetic field inside here is coming out of the board. Now, what about the magnetic field outside the loop? Once my fingers curl out of the loop and they start hitting my hand, which way are they pointing? They're pointing into the page. So the magnetic field outside the loop, and this would be true everywhere, okay, all the way up here, anywhere I put my hand, once my fingers curl out of the page inside the loop, they then go into the page outside the loop. So inside they're coming out, outside they're curling in.